Assalamu alaikum ya shabab. Please listen to this short video carefully. In today's lecture, which you are going probably to see after this, we talked about the second Euler moment of area, which is J. And we discussed J for a hollow cylinder with an outer diameter of d0 and inside diameter of di, and we said that J will be equals to pi over 32 multiplied by d0 square to the power 4 minus di to the power 4. And I told you that I for the same cross section is pi over 64 d0 to the power 4 minus di to the power 4. So it is very clear that J is equal to 2I, which is 2 multiplied by pi over 64 multiplied by d0 to the power 4 di to the power 4, which is going to be the same as pi over 32 d0 to the power 4 minus di to the power 4, so it is equals to J. So indeed twice as I is the same as J. So the question was, is this always true? I think I said true for one student in one section. I said I will check for another section. What I wanted to tell you is that the exact definition of J is the integral of r square dA. Now, this is actually going to be the integral of x square plus y square dA, which is the very definition of ix plus iy. Now, if you remember let me add another so if you remember, for round cross section, it doesn't matter if you take the moment of inertia around x or the moment of inertia around y. So ix equals to iy, which is equal to, for example in here, pi over 64 d to the power 4. So if you want to find J for a solid cross section like this, you will have pi over 64 d to the power 4 plus pi over 64 d to the power 4, and you will end up with pi over 32. Sorry, I made an error here. Pi over 32 d to the power 4. Of course, the diameter here is all of this. This is d. Now, for that reason, when you have a symmetric cross section, okay, you will end up having the relation J equal to 2I only for symmetric cross section. Let me give you a quick example. If we have a rectangle, not square, okay, with this being the base and this being the height, okay, then and this one is x and this one is y. So what is ix, what is iy, and what is j? J for this cross section, which is equal to ix plus iy, is equal to bh cubed divided by 12 plus h b cubed divided by 12. So you will end up with bh divided by 12 multiplied by b square plus h square. This is definitely not the same. So for this case, j is not the same as twice as I. Do you get that? This is all because the section is not symmetric. But you can, somebody would guess that for a square a, you will get the same relation. You will get j equals to twice as I. Okay, I hope this is very clear.
Okay, Assalamu alaikum, ya shabab. Can you hear me?
Yes.
You are breaking.
Yes, doctor, we can hear you.
Okay, welcome back, ya shabab, to the class. Before we get started, I would like to tell you that we have assigned a project and it is already posted. I actually was supposed to post it 1 day earlier. So let me quickly show you the project, and just for a minute, okay? You can see the project right now. I don't
Yes.
think that. Yes. Okay. Was it posted like this in the Blackboard? That's funny.
Yes.
Yeah, I need to. I need to repost it again. But let me tell you, ya Shabab, what is this project is all about? Okay, quickly. This project is about designing little parts of a wind turbine. Okay, we think that this is going to be very exciting for you because God knows you may get a job because of this. Or at least you may get involved in some sort of a job assignment that is related to the wind turbine. After working on this project, you will at least know few basic information. Like for example, the idea that wind turbine are huge, truly huge, while this little guy over here, if you look at him standing, an airplane will actually be smaller than this. Big Boeing 747 will be smaller than this. So that's really huge. This is what you are not going to design this size, of course. In the previous years, we had given student an example like this, which is a 5 megawatt, but this one is not. This is called a horizontal axis wind turbine, and the vertical axis means that the rotation will happen along the vertical line, while this one is along a horizontal line, which is coming out of the page. Now, the turbine can rotate to orient the blade always facing the wind. This is called the yaw axis. This part, which is like a huge room, you can go there and live there as well, probably, especially for a huge turbine. This is called the nacelles, okay? And inside it, there is the low-speed shaft, which you are going to design, okay? And of course, the rotor, the blades, there is also the high-speed shaft, which basically is connected. So basically, this rotation is going to be converted into high speed through a gear in order to generate electricity. The specifications are given to you. This is 500 kilowatt wind turbine, okay? The maximum available these days is a 5 mega. 5 mega, okay? This is half a mega. And you see the forces, the loads in terms of mass. You're talking about something really huge. This is an example of what the forces. Of course, there are other forces that we are not including. So I don't want you to believe that everything here you see is what is exactly there. There is a lot of this in reality, but we are trying to make it a little bit easy for you. What you should know is that this tower is made up of 3 columns, and they are screwed together. In chapter 8, inshallah, ya shabab, we will teach you how to design screws, bolts, yani. And these are the forces. So this is the screws, the bolts, how they are attached to each other. These are the project requirement, and we're trying to encourage you to use softwares to do some stuff. So don't feel hesitant not to use them. Just go ahead anytime you want. And okay, just all right. And we are actually giving you bonuses for using finite element, which is SolidWorks, how to perform finite element. If you go to YouTube and search about SolidWorks stress analysis, you will find a lot of nice simple tutorials that will explain to you how to do this. And if you do this, you will be a step further into being a professional stress analyst or you know, a mechanical engineering designer. Okay. The format, you should have a cover page, you should put the task distribution, the final result, if you have appendices. This is how a shaft could look like. These are some extra material to encourage you. And here I'm telling you, you can go to YouTube to perform stress analysis. This article was published a few years ago, just to show you the magnitude and the direction of the kingdom. This was in 2017. I think there are more initiatives to build a wind turbine farm here in Saudi Arabia. So this is a new business. This is very interesting. And by the way, I would like to inform you that to some extent, most of these values are good. You know, good means they are not absolute true, but they are really good. Yeah, يعني يا أخوان, these values are not joke. I mean, we didn't just put value to make it easy or difficult. These are reasonable value we obtained from manufacturer and papers and research and so on. So we tried our best to make it in somehow suitable to your level. Okay, Shabab? I think this is enough. What I am gonna ask you later through the Blackboard is to send me your team formation. Okay, I need to know who are the teams. I don't know, ya Shabab, if you know each other, but what can I do? During the coming day, I can start sharing your emails, you know, the ID, so you can email each other. And maybe I can make a forum within the Blackboard so you can use it and post that, يا شباب أبغى أسوي group أنا لحالي أنا كذا. You get my point? And hopefully you will team up as 2 to 3 students each team. Okay? I hope this is clear. I'm gonna reproduce. I don't know why the font is like this. I'm going to fix it.
Can I team up with another student in your 12th clock section or only my section?
I think it is better to stick you with the same section, ya Shabab.
Okay.
But let me think. It's okay. If you want to team up with other students, it's okay from my other section. It's fine.
Okay, thank you, Doctor.
Welcome. Okay. Okay, Shabab. Today we are going to talk about torsion. We spoke about torsion in the past few lectures, and we said that torsion is usually applied by the application of a moment acting along the axial direction. And if you see what happened over here is that this rectangle A or square A, B, C, D, after torsion, okay, it got deformed into this shape. This is A, D, B star, just to distinguish them from each other. So indeed, torsion deforms the body in a way that it changes the angles. if you look at the body as pieces stick together, then it will twist the body in a way it will change the angle. This is different than tension, because if you apply tension, then A, B, C might go like that. If you apply tension, this is A, D, B, C, okay? So it will get longer. That's what's gonna happen. Now, what we need to know is that torsion is applied as a moment. If the direction of the moment, using the right hand rule, is as such that the thumb is pointing toward the x-axis, and the outward normal of the surface, this is the surface. If the thumb is pointing toward the outward normal, then this is positive. So with respect to this surface, a positive moment is in this direction. With respect to this surface, a positive moment is in the opposite direction. What matters is that this is always pointing outward of the surface. Now, if you look at torsion from the inside, you will see that it is represented by these swirling arrows that seems like they are rotating, because this is the kind of action which is we feel. I used, when we had student here in the classroom, tell the student about the experiment we do in the class, and I tell them, how do you know that you feel the torsion? Well, it's very simple. If you pull your finger with your other hand, it's totally different than when you twist your finger. Okay? لما كنا يا شباب أطفال في المدرسة، كانت وزارة التعليم تقول أخذ الولد من بيت أهله لحم ورجعه عند أهله عظم، فكانوا يطقوننا طق الجهل. Okay? And I remember one teacher loves torsion a lot. He liked it so much. كان يجي مسكين ياخذ الطالب، هو طبعا المدرس عملاق والطالب طفل في اولى ابتدائي ثاني ابتدائي، يد الطالب ما تجي طول صبع المدرس. But anyway, that monster مدرس will take the student and hold his arm. الارم يا شباب اللي ما بين اليد والمفصل، اوكي، حق المرفق. And then he put his hand on that little tiny arm and started twisting. He's basically torturing the kids by torque. Torsion. He loved torsion a lot. So if you do that to yourself, you will feel the pain, and it is totally different than if you ask your brother or your neighbor or your friend to just pull your hand. It's totally different. It's like you are somehow peeling the skin of your hand in a totally different way. That's not very nice in the morning, but this is what happened to us when we were kids. So if you remember from civil engineering, they told you that there is a relation between theta, which is the angle of a twist, the torque, and the length, and G, which is the shear modulus, and J. Now, maybe I shouldn't have used black, but in a simple term, the way you look at this equation, okay, is the following. You can imagine that theta as an angle will increase if you twist more. As the torque goes more, the theta will be larger. Very simple. And with respect to this, ya shabab, this is, by the way, L. And maybe I should use, capital, but anyway. Here, this is L, small letter, L. It's the length. what is this has to do with the theta? Well, you might take a little piece like this, which is like 10 centimeter, try to twist it, it is impossible. But what you can do is to take the same diameter with very, very long bar, and then with the same torque, you twist it, and it becomes easier to twist. Why is that? Because you changed the length. So length, as you increase it, the angle of a twist will increase. J is inversely proportion, G I mean, and J. G is the shear modulus. The shear modulus, ya shabab, is similar to the tensile modulus. When you twist something, it will behave in an, same fashion. It will have an elastic region. This slope, we call it G, just similar to sigma and epsilon, okay? When we say that this slope is E. Do you get that? J is the polar second moment of area, which is similar to the moment of inertia. You will see actually that they are very, very close friends, okay, in a minute. Just to give you the insight, J is actually twice as I, as simple as that. So if you know I, multiply it by 2, and you will get J. Good? Now, so what is the shear stress? The shear stress, as I explained earlier, ya akhwan, is related to, so this is the radius, rho, the J, which is a property of the cross-section, and of course the applied torque. Good? Now, when rho is maximum, we call it C. So this one, we call it C. Sometimes we call it R. I don't care. I want you to understand that in here, we are defining R as the longest distance from the center to the surface of the shaft. What is the second polar moment of area? This is a very simple explanation if you want to go through it, but in a simple term, J is actually related to I. For example, I for a hollow cross-section with a diameter d0 and di is equal to pi over 64 d0 to the power 4 minus di to the power 4. If you multiply this by 2, you will have 2 gone with 64 as 32, and this is what you get. You get J equals to pi over 32 d0 to the power 4 minus di to the power 4. Okay, very simple. Now, what you should focus on is that torque, in many ways, very important when it comes to power, because in machinery, we tend to rotate in order to produce power. So for example, while steam turbine use the hot air, superheated air, in order to rotate, the purpose of initially burning the air so it goes as superheated, as this is what they taught you in thermodynamics, okay, is to make this shaft rotate. And then we use coupling to couple this shaft with another equipment, which is called a generator. Generator will make you electricity, volt. Now, so in some sense, the relation between torque and power, rotation and power, is very much linked together. So this relation is in here is very useful. You will use it in your project because the wind turbine is just same as that. But we don't, in wind turbine, we don't superheat anything. We put the blades, and when the wind blow, they cause rotation. That's it. And in that rotation, okay, we convert it into electricity. So H, which is the power as a horsepower, is related to the force by velocity. Look, this is the force, this is the velocity divided by a factor of 33,000. Okay, this is the same as this, same as this, same as this, expressed in terms of different parameters. So for example, this is the torque in pound inch, and N is the RPM, revolution per minute. Now, most of the time, we tend to use SI unit and SI unit. And SI unit, in SI unit, the power is related to the torque multiplied by omega. Omega is the angular velocity. You get that? So the power will be in watts, just like the turbine. The wind turbine is 500 kilowatts, is equal to some torque multiplied by angular velocity, which is measured in radian per second. Good. So يا اخوان الان لما يجي في الدعايات ويقول لكم انه اليوكن or Land Rover or Land Cruiser with 450 horsepower, that will tell you exactly how much power you are putting there in horsepower unit. And then by knowing how much is the rotation, the RPM at a given time in the while you are driving the car, you can calculate the torque. That's it. Okay. Now, I'm not going to talk a lot about this, but I think those who go يحبون التطعيس يا شباب يدرون ايش معنى انه يقول لك حط السيارة على الثقيل يسموه. Okay. And what does that mean? Basically, you are using the transmission, الجير, انه يطلع على gear number 1 لانه انت عندك multiple gears. The bigger the gear, the higher the speed. That's why when ايام يا شباب السيارات كثير كان منتشر الجير المانيوال العادي. And I don't know if you know how to drive the car, but you have to drive it such that you switch from number 1 to 2 to 3 to 4 to 5. When you reach 5, you can drive in the highway 150 kilometers, no problem. But if you put the gear on 1 and you push the gas as much as you can, تسمع الانجن يصرخ والصوت عالي، أن السيارة ما تمشي أكثر من 20-30 kilometers per hour. And if you continue doing that, بالمصطلح العام, you are burning your gearbox. The idea is this: لما تحتاج speed ما تحتاج torque. لما تحتاج تطعيس تمشي على الرمل يا شباب, you need torque. That's why يسموه ثقيل, لأنه السيارة feel like heavy. It doesn't speed up much, but it will give you good torque that will allow the car to be driven over the stand. بس أهم شيء لا تنسون, this is not the trick. يعني مو تروح الحين وتحطها على الأول وتمشي, لازم شوية تنزل الضغط حق الكفرات, لا تنسون. Now, this is pretty much everything I can tell you about torque. This is now an example that we are going to solve together. But before we do that, let me, ya shabab, ask you kindly to turn on your webcam. We're going to take that in this. Okay. Faisal?
Yes, present.
Faisal, Abu Sa. Okay, thank you, Faisal. Yusuf? Abu Yusuf, talk, yeah. Hamad?
Yes.
Where are you, Hamad? I can see you. Ali القحطاني? Ali? I thought.
هير دكتور هير سوري.
Okay. يوسف اليوسف.
موجود دكتور.
Okay. العباد.
Yes, I'm here.
يا علي العلي حسين.
Yes, doctor.
محمد.
موجود.
Where are you? Okay. حسن.
Yes, موجود.
Yes. مبارك.
Yes.
مبارك. أحمد.
Yes, here.
علي.
موجود دكتور.
اوكي. معجب.
موجود دكتور.
سلطان.
موجود يا دكتور.
اوكي. عبد الله. حجاب.
Yes.
اوكي. سلطان.
موجود.
اوكي. فارس.
Yes.
عبد الرحمن.
يس.
خالد.
موجود دكتور.
اوكي. عبد الله عوفي.
موجود.
فارس. يا ثابت. Where is ثابت? علي رمضان.
موجود.
اوكي. هاشم.
موجود.
ماجد.
موجود.
محمد.
يس دكتور.
يا محمد, I don't think you came early today. Last class you told me that you get disconnected and you came, and you are doing this every time.
No دكتور, just this time. I was late.
Okay, I'm watching you. Sultan, Ahmed.
Yes, doctor.
مشعل. Yami.
Yes دكتور.
Where are you, Mishal? I'm trying to find you. Can you talk?
Yes دكتور, I'm here.
Yeah, Mishal, you cannot change your name and your picture. I'm gonna make another announcement for this. Walid.
Yes, doctor.
Okay. Muhammad.
Yes, doctor.
Barish. Okay. Abdullah.
Yes, doctor.
And Ahmed.
Yes, doctor.
Okay, thank you so much. شوفوا شباب, أنا راح أسوي الإعلان اليوم for Thursday class. Anyone who doesn't change his name correctly and put his own picture, I'm not gonna admit him in the class, okay? I'm gonna send you, inshallah, today the instruction how to do that. I am not asking you to come at night. I am not asking you to do anything weird. It's very simple. I think it is يعني legit يا شباب to ask you this. Okay. Now let's move on to. Can you see my screen يا شباب؟
Yes.
It's the laptop screen.
Okay. Okay, so we have this example. Let's see how. It's very simple example. It's not very complex. So we have a solid propeller shaft on a ship extend outward from the hull. During operation, it turns at an omega of 15 radian per second when the engine develops 900 kilowatts of power. This this causes a thrust, I mean, of 1.23 mega Newton on the shaft. The thrust طبعا يا شباب هو البربس صح؟ الثراست اللي قاعد يصير بأنه from Bernoulli relation when the propeller rotates it disturbs the water around it making a lower pressure. The volume of the ocean will push against that void which has a lower pressure, thus generating a push, a force. This force is measured in 1.23 mega Newton. All of this mega Newton force is trying to make the ship, a tanker, whatever it is, moves forward in the water. If the shaft has an outer diameter of 250 millimeter, calculate the maximum normal and the shear stresses on the shaft. Okay, so this is what we want. If you look here, I think I have the information. I'm gonna just in a minute. Okay, so the power was given to us P as 0.9 multiplied by 10 to the power 6 watt, which was how much? It was given to us as 900 kilowatt. That was the power. So this one is the power in watt. Now, from the relation torque equal to power divided by omega, لأنه احنا كان عندنا relation P equals to omega T. So we can get 0.9 multiplied by 10 to the power 6 divided by how much? 15. Because omega is in radian per second. This one is in watt. This one is in watt, and this one will become in Newton meter. So what is the result? It is 60 multiplied by 10 to the power 3 Newton meter. Now, we have been asked to find the normal and the shear stress. So for the normal stress, we will need the area. Area is equals to pi over 4 d square, which is equal to pi over 4. The diameter was 250 millimeter. So this is 0.25 and square. So you will get the area as 0.0491 meter square. The J, which is the polar moment of inertia, moment of area, I mean, this is pi over 32 d0 to the power 4. Remember, there is no di, so di is 0 because I showed you earlier J for a hollow section, which is pi over 32 d0 to the power 4 minus di to the power 4. That's what I did. So in here, this one is equals to 0. So from this, you will get 0.3835 multiplied by 10 to the power minus 3 meter to the power 4. Now, since this is a thrust force, it will actually cause compression on the shaft. So the shaft will have sigma equal to F over A, which is a negative 1.23. It was mega Newton, so it is 10 to the power 6 as a Newton, divided by the area, which is 0.0491 meter. And what you will get minus 25.06 megapascal. For tau maximum, we will have T, the torque, multiplied by C or R, whatever you want to call it. Here, it is 60 multiplied by 10 to the power 3 as a Newton meter. C is the radius. Now, if the diameter is 250 millimeter, then half of it is 125, which is 0.125 meter, divided by the J, which is equal to 0.3835 multiplied by 10 to the power minus 3. And what you will get, 19.56 megapascal. Good, يا أخوان. Good.
دكتور عندي سؤال.
Yes.
الحين السيركلر بارت مو في هولو؟
لا ما في. هذا this one is not. No, هذا حق البيلر نفسها. البروبيلر. احنا we're talking about the shaft.
اوكي تمام.
Okay. Any other question? Okay. Let me ease it up. Yes.
What about the length? You didn't use it, or it's not necessary?
Yeah. هذا اللي ورطكم صح؟
Yes.
Yeah. It. Why? لو مثلا أنا قلت لك إنه find the angle of a twist, which is TL over JG, something like that, you will use that link. But I didn't. I know maybe in the figure I should remove the link, but يعني أنت ما تقدر تجبر المعادلات على شيء يا فارس.
صحيح.
It is what it is. Okay?
Okay.
All right. Now, within the next 3 minutes, let's start talking about the three-dimensional stress state. The reason why we are doing this is to teach you the convention of the naming for the stresses. لما تكلمنا في البداية قلنا بأنه stress is the second order tensor. And tensor is different than vector. And I'm just going to make it so easy on you. If you want to write a tensor, sigma, beta, whatever it is, anything which is a tensor, it must have two indices دائما. هذا اسمه second order tensor. عشان كذا هو في two indices. تجي تسألني تقول لي في higher tensors؟ أقول لك yes. There are fourth order tensors, and you need to put for that fourth order tensor 4 indices. But this is too much. أبقى بعد الحين ترتاعون علينا يا شباب ولا حاجة. يجيكم بطنكم. المهم إنه what is the idea here is that the first index represent the face. The second index represent the direction. What does that mean? It means the following. إذا كان عندنا cube يا أخوان like this, we established coordinate system like this, In mathematics, we name the faces, the surfaces by sorry, this is gonna flip your mind, ya akhwan. It's just my iPad. Come on. Yeah. So a surface is identified by its normal. فمثلا النورمال على هذا السيرفيس هو الاكس اكسس، فهذا هو الاكس فيس. Similarly, this is the y face. Similarly, this is the z face. So, in 1 second, if we know the face, the direction is the same direction as the arrow. So, this is a direction x. فإذا سيجما XX هو الستريس اللي منطلق من الفيس X باتجاه الإكس. لو عملت shear like this، هذا الشير موجود على which face؟ face X. Where is the direction؟ Y. صح ولا لا؟ And that's it. Very simple. We'll continue this in the next class, inshallah. Thank you so much.